And we're on. Fish on. Okay. So let me just make sure that this is sounding all right. It sounds all right to me. So we're going to do some paper reading today. Let me just mute this. Get the chat out. Boom. It's going to be a relatively short stream. I've only got about just over an hour. So let's get a timer. But this is exciting new paper. So I think an hour and 20 minutes will be good enough to go through this. We can go through it again in another stream. But, so this is self-supervised learning. The first high-performance self-supervised learning algorithm that works for speech, vision, and text. Let's get a Notion document up. We'll go into code. Self-supervised learning.
SWB audio capture
Papers.
not registered.
I'm learning all about self-supervised learning at the moment. So this is an exciting new paper. Let's go data2vec using self-supervised learning across multiple modalities. Vision, text, audio. Wonderful. Chat popped out. So this is what we're doing today. We're going to read this. And maybe I get some notes in here. Papers. Can I turn this into a page? Now, let's go paper. So yeah, let's have a look at this. Am I on the screen? You can see everything? Beautiful. So self-supervised learning, where machines learn by directly observing the environment rather than being explicitly taught through labeled images, text, audio, and other data sources, has powered many significant recent advances in AI. SG, hey, love from India. Love from Australia, my friend. But while people appear to learn in a similar way, regardless of how they get information, whether they use sight, sound, for example, there are currently big differences in the way self-supervised learning algorithms learn from images, speech, text, and other modalities. Yeah. So what the main addition that this paper brings is data2vec. So this discrepancy has been a significant barrier to applying advances in self-supervised learning more broadly because a powerful algorithm designed for, say, understanding images can't be directly applied to another modality such as text. It is difficult to push several modalities ahead at the same rate. So let's go get the paper. Hey. And code. So the code's on GitHub. I'd like to have a look at the code too. So goal, want a unified learning mechanism for multiple modalities, e.g. vision, text, audio. So if we jump into the paper, yeah, here's what happens. Here's the main graphic of it all. So let's copy this, and then we can talk about it. So here's what happens. I just need to turn my fan up because it is extremely hot here.
SWB audio
Australia.
capture not registered.
Beautiful. Oh, look at this. I like tea with milk, and I'm drinking tea with milk. If that's not a thumbnail, I don't know what is. But here's what happens with data2vec. So the input goes into a teacher model, the original, and the teacher model creates some sort of representation of that. It creates an embedding. And the teacher mode, so there's two models that are operating in sync here. The teacher model gets the full input of the image, the speech, the language, whatnot, creates a representation of that. The representation could just be a big tensor of numbers. And then the student model gets a masked representation of that. And now, from what I remember reading, for the images, it's about 60%. Yeah, different to their work, we found it useful to mask 60% of the patches instead of 40%. We use randomly applied resize image crops, horizontal flipping, etc. So they mask, in the vision, they mask 60% of the image into the student model. The audio, I think they mask like 10 frames or something like that at a time, 10 timestamps. And then natural language, they're masking out, similar to the BERT paper, they're masking out 15% of words randomly. So what the student model tries to do is, here we go, the model first produces representations of the original input example, teacher mode, which are then regressed by the same model, so these two are the same architecture, based on a masked version of the input. So the student mode tries to predict the teacher mode representations, except the teacher mode representations are unmasked, whereas the student inputs are masked. So the student has not as much information as the teacher. So rather than trying to, so this is, they use all three, the same learning modality or the same learning mechanism across images, speech, language. So this is different to other previous attempts at self-supervised learning. The teacher parameters are an exponentially moving average of the student weights. The student predicts the average of the K network layers of the teacher. So these are layers in the student network, and it's trying to predict the average of these layers in the teacher network. And the teacher tracks to see how well the student's going. I love this learning paradigm. It's because that's quite similar to how you would learn in real life, right? It's like you might have a teacher teaching you something, and they know, let's say, the answer, and then they say, hey, here's the blank jumped over the fence, fill in the gaps. And from your knowledge, you probably won't say the tree jumped over the fence. You might say the dog jumped over the fence, or the cat jumped over the fence, which is fill in the blank. That's essentially, this is a whole big game of hide and seek here. So we can go through the paper. Yeah, masking. Model architecture, so they use the transformer architecture. What we're going to do, maybe we'll read the blog post, read a little bit of the paper, and then come in and have a look at the code.
SWB audio capture not registered.
Is this the whole thing? Okay, so the vision model isn't there yet. That's all right. Let's read the paper. Sorry, the blog post. How data2vec works. Much of AI is still based on supervised learning, which works exclusively with labeled data, but it's simply not possible to collect labeled data for all of the things we would like machines to do. For example, while researchers have done a lot of work in creating large-scale labeled datasets for English speech and text, it's not feasible to do this for the literally thousands of spoken languages on the planet. Gaurav, what's going on? SG, you are doing amazing work on Nutrify. Keep going. I love to watch you working on Nutrify. Oh, don't worry, I'm going to be making plenty more videos on Nutrify. Self-supervision enables computers to learn about the world just by observing it and figuring it out. Having machines that don't need to be explicitly taught to classify images or understand spoken language is simply much more scalable. Yes, so that's
registered.
That's self-supervised learning in a nutshell, right? Let's write that down. Problem. Supervised learning, data and labels is not scalable. As in, you can't just keep labeling more and more data. Well, you can, but you'll be chasing your own tail. Because as data increases, a number of labels needs to increase, and the spiral will never end. So, in an attempt to fix this scalability issue, self-supervised learning comes in to learn representations, comes in as a method for algorithms to learn representations from the data, representations of the data from the data itself, rather than using data and labels as a base. Gaurav, yes, I am working on a PyTorch course. It's a work in progress. There's going to be a fair few more updates
SWB audio capture
months.
not registered.
So let's go there. Recently, there have been many different forms of self-supervised learning methods emerge. However, there has yet to been, they often use different learning mechanisms for different modalities of data, e.g. different for images, text, or for vision. For vision, speech, and language. Data2vec differs by using the same learning mechanism, teacher and student, where the teacher has the full representation of data and the student tries to predict the full representation based on a masked version of the data. Okay, there's data2vec. So let's go back to the blog post and see if we're on the right path. How data2vec works. Much of AI is still based on supervised learning. Yes, we've read that. Research in self-supervised learning today is almost always focused on one particular modality. Modality being, let's write a little glossary down here. Glossary, modality equals type of data you're working with, e.g. images for vision, text for language, WAV files for sound. Type of data, let's just go e.g. vision, language, speech, sound. So researchers working on one modality often take a very different approach from those working on another. For text, researchers train models to fill in blanks in sentences. Speech models, however, need to learn an inventory of the basic sounds of speech in order to predict missing sounds. In computer vision, models are often trained to assign similar representations to a color image of a cow and the same image flipped upside down, so it associates the two much more closely than it would with an unrelated image such as that of a duck. Okay. So usually in computer vision, models are often trained to assign similar representations to a color image of a cow and the same image flipped upside down. So that's using data augmentation to create a self-supervised learning approach. So you have one image of a cow that's just color, and then you flip that image and turn it into black and white, and it's saying, well, if you have that image of a cow that's in color and you have the same image but it's flipped upside down and in black and white, it's still the same cow. So traditionally, it'd be taught to treat those two images as the same. However, we've got a different approach here. Algorithms also predict different units for each modality. Pixels or visual tokens for images, words for text, and learned inventories of sounds for speech. A collection of pixels is very different from an audio waveform or a passage of text. And because of this, algorithm design has been tied to a specific modality. This means that the algorithms are still functioning differently in each modality. Yes, that's what we want. So that's what we want, a unified learning mechanism for multiple modalities. So this is data2vec. Can I copy this image? Animated version of data2. Oh, lost my keyboard. So data2vec simplifies this training by training models to predict their own representations of the data. Yes, regardless of the modality. So data2vec simplifies the training approach for self-supervised models across different modalities to predict their own representations. This is the key. This is the most important
capture, not registered
sentence in the whole blog post, I reckon. To predict their own representations regardless of the modality. I like this because think about this. If we're going to go towards general intelligence, artificial general intelligence, whatever that is, I actually don't know what that is. I don't have a definition, but it can't be just going, oh, okay, this model's really good for vision, this is really good for language, this is really good for sound. Like the way we learn, or I feel like we learn, is we learn very similarly across different topics. So as in the way we learn from sound and the way we learn from vision, the way we learn from language, although you may favor one, how we learn for each of them, I'm guessing humans take in all of those inputs and can use all of those inputs simultaneously to derive an understanding of the world. Whereas at the moment, a lot of algorithms in machine learning are specified for one particular modality, such as a CNN would be highly suited for vision. Now, the transformer is kind of changing that because the transformer can do speech, vision, and language. So that's probably this is a beautiful crossover of where things are going. Like in terms of we need to use less data or labeled data to start learning representations of the world, and 2, it'd be great if we could use just a single algorithm type rather than multiple different algorithms to understand those representations, understand different data types. So let's keep going. So by focusing on these representations, the layers of a neural network, instead of predicting visual tokens, words, or sound, a single algorithm can work with completely different types of input. This removes the dependency on modality-specific targets in a learning task. Directly predicting representations is not straightforward, and it required defining a robust normalization of the features for the task that would be reliable in different modalities. Our method uses a teacher network to first compute target representations from an image, a piece of text, or a speech utterance. Next, we mask part of the input and repeat the process with a student network. Yeah, there we go. We mask part of the input, and let me just make some notes. Did that show up? Wonder if this will work now that I've saved it as a GIF. There we go. So method. Teacher network first computes target representations from an image, a piece of text,
SWB
or
audio
a speech
capture not registered.
utterance. Input is then masked, and the process is repeated with a student network, which then predicts the latent representations of the teacher. I like that. I really like that. So the student is just trying to predict what the teacher already knows. There we go. So there's another important line. Student model has to predict representations of the full input data, even though it has a view of only some of the information. Oh, I like that. And then we have here, the teacher network is identical to the student model, but with weights that are slightly out of date. Okay, so I think this is from weight degradation.
SWB
We'll check that in
audio
the paper.
capture not registered.
We tested the method on ImageNet. So it basically outperforms every other existing form of self-supervised learning. On speech, we found that it performed better than data2vec 2 or Hubert, two previous Meta AI self-supervised algorithms for speech. For text, we tested on the popular Glue benchmark suite, and it performed as well as Roberta, a re-implementation of BERT. I think Roberta was about 2019. So an optimized method for pre-training self-supervised NLP systems. So this is the results on computer vision. ImageNet 1K validation accuracy. So yeah, almost or 0.5%, let's say 0.5%. 0.5 to 1% better than this previous state of the art. And a lower word error rate than their previous data2vec 2 and Hubert. data2vec for speech, performance for base models. Oh, that was for speech up there. And then we have data2vec for text. So it basically equals the previous self-supervised baseline. But the important thing is that this is with 3 modalities. So that this isn't different algorithms or different types of learning modalities for vision, for speech, and for text. It's all 3 are using the same learning mechanism. That's this student and teacher mode, which is beautiful. So towards machines that learn from observing the world. While self-supervised learning has made great progress in computer vision, videos, and other individual modalities,
SWB audio capture
through different learning
not
objectives,
registered.
the core idea of this approach is to learn more generally. AI should be able to learn to do many different tasks, including those that are entirely unfamiliar. We want a machine to not only recognize animals shown in its training data, but also adapt to recognize new creatures if we tell it what they look like. data2vec demonstrates that the same self-supervised algorithm can work well in different modalities, and often better than the best existing algorithms. This paves the way for general self-supervised learning and brings us closer to a world where AI might use videos, articles, and audio recordings to learn about complicated subjects, such as the game of soccer or different ways to bake bread. I like this. data2vec demonstrates that the same self-supervised learning algorithm can work well in different modalities, and often better than the best existing algorithms. We also hope data2vec will bring us closer to a world where computers need very little labeled data in order to accomplish tasks. Since it is difficult and sometimes impossible to collect annotated examples to train speech recognition models for thousands of languages, for example, data2vec is an important step toward more general AI. This project complements research on more general architectures. Yeah, I think this is the perceiver architecture here. Yeah. Perceiver, general perception with iterative attention. So now we have perceiver. So perceiver architecture equals a general
audio capture
architecture
not registered.
For learning across modalities. Let's write this. There seems to be a convergence of general methods for different modalities, both in the architecture sense and in the learning sense. And then we have data2vec equals a general learning mechanism for self-supervised learning across modalities. So that's a cool part is now we have a general architecture for learning across different modalities or creating representations across different modalities, and now there's a general learning mechanism. So the difference between data2vec is that it uses, depending on whether it's speech or images or text, to create this teacher mode representation, it uses a slightly different architecture. So now that's where we can jump back into the paper. And I'm just going to open something over here. I'm just going to write a note down. I just had an idea. I'm going to come back to it later.
SWB audio capture, not registered.
Beautiful. Don't want that. I want this. And I want this. So here we go. I'm not going to read through the whole paper. You can do that if you want. I'm just going to jump in just to some of the highlights of, let's go computer vision. Data2vec, computer vision. Here we go. So they use the standard transformer architecture with a modality-specific encoding of the input data borrowed from prior work. So standard model architecture. Let's go to this actually. We want model architecture. So overall architecture is the standard transformer architecture with a modality specific encoding of the input data, e.g. transformer
SWB audio capture,
flavored for
not registered.
vision, text, or speech. But it's, yeah, for computer vision we use the VIT, so the vision transformer strategy of encoding. Can I zoom in on this? There we go. For computer vision, we use the VIT strategy of encoding an image as a sequence of patches, each spanning 16 by 16 pixels into a linear transformation. So let's write down this. VIT strategy of encoding an image as a sequence of patches, each spanning 16 by 16 pixels. Input into a linear transformation. And what's bow? BERT pre-training of image transformers. Let's have a look at this. Vision transformer. Vision transformer paper.
SWB audio capture.
Yeah, I remember this one.
Not registered.
Vision transformer. And this is BERT pre-training of image transformers. So what happens here? Data preparation. So we introduce a self-supervised representation model, BERT, which stands for bidirectional encoder representation from image transformers, following BERT developed in the natural language processing area. So we proposed a masked image modeling task to pre-train vision transformers. Specifically, each image has two views in our pre-training, i.e. image patches, such as 16 by 16 pixels, and visual tokens, i.e. discrete tokens. We first tokenize the original image into visual tokens, then we randomly mask some image patches and feed them into the backbone transformer. The pre-training objective is to recover the original visual tokens based on the corrupted image patches. So this is the pre-training objective, to recover the original visual tokens based on the corrupted image patches. After pre-training BERT, we directly fine-tune the model parameters on downstream tasks by appending task layers upon the pre-trained encoder. Experimental results on image classification and semantic segmentation so that our model achieves competitive results with previous training methods. For example, base size BERT achieves 83.2 top 1 accuracy on ImageNet 1K. Significant outperforming from scratch BERT training with 81.8% with the same setup. Moreover, large BERT obtains 86.3 using only ImageNet 1K, even outperforming VERT L with supervised pre-training on ImageNet 22K. Oh. Code and pre-trained models are available from there. Pseudomaze, what's going on? What sound? Is it like a rustling? Maybe it's my fan. Maybe it's my fan. Can you still hear? Let me know if you've got like something going on, but it's probably my fan in the background. Oh, was that robot? Was that robot saying SWB audio app is not something like that? SWB audio app is not authorized. I need to delete that crap. I was trying to play the sound from my computer one time, and this thing has installed like some weird kernel that runs no matter what. Like, I tried to record the audio that was coming out of my computer and play it on the stream, and it worked, and I paid for it, the $12 or something for a year, and now it's saying that it's unregistered even though I paid for it. So, go figure. the only way to remove it is to completely delete it from the computer. So the code is here. Bayet. Do they have a picture? Hey, look at this. I need to delete that. So thank you for letting me know that that's there. Okay, so this is... And yes, I have read conv next. I'm going to explore that in a future stream when I finally upgrade my transformers. I mean, sorry, my ResNet. Conv next. So what I'm going to do is I'm going to come back to the half finished repository that I did for ResNet, or not even half finished, but just a PyTorch ResNet implementation. I need to fix this. Status. I'm going to add it here for a node. Thank you for that. Status, and if you're wondering, conv next is like the latest state of the art in computer vision and convolutional neural networks. So, or just pure computer vision, that is. But right now we're looking at self-supervised learning. So status, code broken. Going to come back and look how to add conv next features. Is it saying SWB audio app is not? Well, that's going to exist for the rest of this stream because I'm going to delete it after. Let me just add that to my list of to-dos today. Delete SWB audio app. I can mute it from OBS. Okay, this is what OBS looks like. There we go. So computer audio fully muted. Audio fully muted. All that should be coming out is the Shure SM7B. And system preferences. Look, I'll show you this app. Output there. There's that app, SWB audio. So we should be muted now, but let's go back to the paper. I've got about 25 minutes or so left. Thank you for that, letting me know. So they use for vision, they use the BERT image transformer style encoding. Here we go. Oh no, that's for sound. After the input sample has been embedded as a sequence of tokens, we mask part of these units by replacing them with a... Oh my goodness. For computer vision, we follow the masking strategy of Bao et al. 2021, which is this one. No, sorry. This one. Masking strategy. So this is what the student uses. For the student is the same as the masking strategy in and let's just put an image, a nice image here. So this is, they turn an image into these patches. See how this image is now a square and then it gets broken down into 4x4 patches? That's the essence of vision transformers. I want to see the code. Masking generator. And how does the encoder here look? Import atta. What is Python atta? Anyone know what Python atta is? I like this. Has anyone seen this? Help you to write correct and self-documenting code. Beautiful. From attas, import asdict. This is why I like reading like good quality code, because you find out about these things that you wouldn't have otherwise find out. Define class, some class, a number, int, factory. Mask generator. Here we go. Input size. So this is the code that does the mask patches. Is it random? Random. Okay. Is Ross Whiteman an author of this paper? So this is where atta comes into play. I've never seen this in Python code. Group count. I like this. So this has 1, 2, 3, 4, 5 attributes. Ray JU, hello. Wow, accuracy at 5 is 98.6%. I love looking at the training code too. Okay. So we go back to the paper. That's how they do the masking. I want to read more about what attrs does. I like atters. I like that. What's umlim? See, so many beautiful discoveries when you just go exploring. Large-scale self-supervised pre-training across modalities. Oh. When did this paper come out? I just stumbled upon a great repository. Let's star this. We present a unified vision language pre-trained model VLMO that jointly learns a dual encoder and fusion encoder with a modular transformer network. Mixture of modality experts transformer where each block contains a pool of modality specific experts and a shared attention layer. Because of the modeling flexibility of MOMI, pre-trained VLMO can be fine-tuned as a fusion encoder for vision language classification tasks. Moreover, we propose a stage-wide pre-training strategy which effectively leverages large-scale image-only and text-only data. Oh my gosh, there's too much to read here. Standard machine learning practice. Where were we? Back to the Facebook paper. Okay, and so they use... So I'm not going to go through... we've done vision. So it does a vision... That's a computer vision. It does a VIT strategy of encoding an image for the teacher model. And the student model, they use the same. The student model, however, has the masked encoding version of the teacher model. And so this is what the mask encoding strategy is for the student model of data2vec. And then, so that's, so that where they have the same learning strategy across each modality, but they have a different way of representing the data for each strategy. So each modality, sorry. So that's where the value could be in combining the perceiver architecture, which is a transformer architecture or a adjusted transformer architecture for learning across different modalities, with the data2vec, which is a general learning mechanism. So let's highlight this. That would be cool. And so for... Yeah, so they use, for language, they mask the tokens. Here we go, 4. Experimental setup. So computer vision, we embed images of 224 by 224 pixels into patches of 16 by 16 pixels each. Each patch is linearly transformed and a sequence of 196 representations is input to a standard transformer. So instead of 40% of patches mass, note, data2vec uses 60% of patches masked. We use randomly applied resize image crops, horizontal flipping, and color jittering. What's color jittering? Which is what they use in here. Look how much. That's how deep you get after color jittering. Here we go. Our rotation policy includes randomized resize cropping, horizontal flipping, and color jittering. What is color jittering? Wu et al. Deep learning. What is color? Okay, beautiful. Color jitter. Randomly change the brightness, contrast, and saturation of an image. Data.org. And use the same modified image both for the teacher and student mode. Models are pre-trained for 800 epochs. As batch size, we use 2048 for VIT big and 8192 for VIT large. We use the atom optimizer and a cosine schedule with a single cycle where we warm up the learning rate for 40 epochs to 0.002 for VIT-B and 80 epochs to 001 for VIT-L. After which the learning rate is annealed by the following cosine schedule. Okay, so this is its training methodology. And then on the top, for image classification, we mean pull the output of the last transformer block over all patches and input this into a softmax normalized projection performing the classification. So they use, softmax softmax linear layer, which does the classification. We fine-tune VITB for 100 epochs and VITL for 50 epochs using Atom and a cosine schedule, where we warm up the learning rate for 20 epochs to 0.004. Yeah, so they pre-train it. Let's write this down. Pre-training is done on ImageNet with VITL and VITB. VITL for various schedules. Pre-training happens for longer epochs, e.g. on ImageNet with no labels for how long? 800 epochs, but fine-tuning happens less for less time, e.g. on ImageNet with, so when they say fine-tuning, they mean they do on ImageNet with labels for 100 epochs. To 100 epochs. So they're still using labels here. Is it really self-supervised learning? Training targets. Here we go. Yeah, look at this. To evaluate our approach for computer vision, we pre-train data2vec on the images of ImageNet 1K training set and fine-tune the resulting model for classification using the labeled data of the same benchmark. So that's important to note. For evaluation, so you still need all that labeled data. Of 1K. How does it perform with like only 10% of the labels? Predicting so table 1. Yeah, how much I want to know how much of the data they used. Without using extra model weights or supervision, Mark's feet pre-trained on unlabeled videos achieves unprecedented results of 86.7%. Mars feed further generalizes to image input, which can be interpreted as a video with a single frame and attains competitive results on ImageNet. So how much data did these guys use? The vision model isn't even up there yet on the GitHub. What's papers with code say? Browse state of the art. Data2vec's probably not here yet. Is this self-supervised? Is this really self-supervised? Well, there's Dino. Our results show that combining the two techniques, ESVIT achieves top 1 on ImageNet linear probe evaluation. iBot. So 86.3% fine-tuning accuracy for computer vision. How did this one go? This is from ByteDance. Oh. Okay. iBot might take the cake here. They got 81% linear. Where did iBot go? So I think that other implementations looks like iBot from ByteDance performs very similarly, if not better. Oh, using additional training data. Extracting semantic patterns. We extract top k numbered local classes based on patch tokens with their corresponding patches and context by running the following command. This is really cool. So this could play into Nutrify, where you just start What does this look like on Colab? Wow. Align. That's really cool. Okay, so we went through a bunch of stuff to do with data2vec. I've got to rock and roll, but this is really cool. Data2vec using self-supervised learning across multiple modalities. They have a unified learning mechanism across vision, text, and speech. And then we went into a whole bunch of different stuff about, we went down the rabbit hole of self-supervised learning. Like, look at all this. So they use, for vision, they use BERT pre-training of image transformers. For text and speech, they use different methodologies, but that's covered in the paper. Then we learned about attrs in Python, which is apparently the one Python library everyone needs. So I'm excited to read about that because I'd like to get better at writing Python. There's that. That's the paper again. Papers with code, amazing resource. iBot looks like it might outperform data2vec. I'm not sure. Maybe a little bit. Data2vec might be a bit simpler. iBot might use more data. But I'm going to look into those later. And then there was mass feature prediction for self-supervised visual pre-training, which is mass feed. Apparently data2vec outperforms that as well. And that's from Facebook AI research as well. Okay, there we go. They mask it. Beautiful. Masking, and I like this. I like this. Looks like masking is not only powerful in language, but it's starting to get more and more effective in vision and speech. With that being said, I got to bounce. Thank you for tuning into the stream. I will see you next time.